Hello everyone, my name is Ryan O'Leary and today I will go over a set of open source tools we have for working called Fiano. Before we begin, many thanks to everyone who helped make Fiano possible. This includes Ron Minnick, Julian, Andrea, and of course, Gon Shun. A big thank you to all of our contributors as well. UEFI Tool and UEFI Firmware Parser helped us immensely in creating UTK. A big thank you to the authors of these two projects. First, I'm going to explain the motivation behind UTK for a bit. In the pursuit of Linux boot, we firmly often encounter firmware images which are provided without any source. It's not all lost though, because the UEFI spec defines a file system for storing its drivers and other files. As we will show, it is possible to parse this file system and access the files. This has a number of applications, such as inserting Linux boot as a Dixie driver into a firmware image. It allows for rapid prototyping. You could quickly swap out a Dixie that you built in a pre-built image with one that you're using for debugging. Has a couple of security applications, such as removing unnecessary Dixies to reduce the attack surface. It also allows for security forensics. So here you can see the basic workflow of UTK. So UTK stands for UEFI Toolkit. It's one of the tools inside of Fiano, and it's used for parsing UEFI and performing some modifications on it. So first you procure a UEFI image, so you can either build it yourself from open source using Fiano core, or you can use a flash programmer to read it off of a machine flash chip. So once you have your image, you pass it into UTK as the first argument. So this will parse the image, and then you could decide what sorts of operations you want to perform on it. So in this example here, we use replace FFS. This replaces one of the firmware file objects inside of the UEFI image with one on your local file system called bds.ffs. And then we save the image as new EFI.bios. So this is able to read the image, make some modifications to it, and save it back to your file system. And don't worry too much about the syntax you see here. I'll explain it in a bit more depth later on. It'll make more sense. So for those who are unfamiliar with Linux boot, so Linux boot is the practice of adding a Linux kernel to your firmware image. Linux provides a lot of well-written, highly optimized, secure drivers for disk operations and for net booting, and I guess network in general. And we have on top of these a few applications ready to go, such as our netboot application and disk boot, which you can use to replace common drivers in UEFI such as Pixie boot, etc. So the main mantra for us is let Linux do it, since Linux already has the high performance drivers. It's already very well maintained. So to use UTK to insert a Linux boot kernel into a existing firmware image, you would use the same set of operations. You'd use the replace PE32, and this example here replaces the shell with a Linux EFI image. So Linux, when you build it, has an option to build it as a EFI application. And then when the UEFI BIOS goes to run this file, it's a UEFI application. It thinks it's running the shell, it actually runs Linux, and then Linux calls exit boot services and takes the machine away. So here, so once you have Linux boot in the firmware, you can start removing unnecessary drivers. Since Linux has an implementation for networking, for disk drivers, for USB stacks, a lot of the drivers inside of UEFI are made redundant. So we developed this tool called Dixie Cleaner to help you automate that process of removing Dixies. Essentially, Dixie Cleaner iterates through each driver. Some firmware images have over 400 Dixies. Dixie Cleaner goes through each driver one by one to determine if it is necessary. So first it attempts to remove the Dixie and flashes the resulting image onto a machine to see if it still boots. So if it does still boot, the driver can be safely removed, and it continues iterating over the remaining drivers. But if it doesn't boot, the driver is considered load-bearing and cannot be removed. So in the context of UEFI, you could think of a Dixie as synonymous with the term driver. It's basically a driver present inside of the UEFI file system. So these load-bearing Dixies, you could, after the fact, you can manually look at them. Oftentimes there's some simple reason why they couldn't be removed that you could fix with a bit of code, or it could have a dependency on another driver being removed first. That's why we often run the Dixie Cleaner in multiple iterations. We keep running it until an iteration occurs where no Dixie is removed. So you perform multiple passes of the Dixie Cleaner. And I'll give you a short demo of the Dixie Cleaner running here. So for each Dixie Cleaner run, there is a shell script. It doesn't necessarily have to, it just has to be any application, but in this case it's a shell script which tests that the UEFI image, the modified UEFI image with the Dixie removed, is able to boot successfully. So in this demo, we are using the OVMF firmware image from UDK2, which can run inside of QEMU. So to test to make sure the image still boots, we boot it inside of QEMU. And the reason we do this for the demo is QEMU is able to boot images fairly quickly. It doesn't have to do much machine setup. So you can see here we run it in QEMU, and then we grep for this expression shell. So if the serial contains the word shell, that means it booted into Linux. Linux prints shell once it boots. And then if it doesn't contain that token shell, we return exit status 2, which indicates to Dixie Cleaner that the machine didn't boot if it doesn't contain the token. If it does contain the token, it returns exit status 0. So in the invocation to UTK, we pass in the BIOS, we give it the Dixie Cleaner command, we give it the shell script. So you can see here, on the first round, it's trying to remove this Dixie, and success. So it was able to successfully boot in QEMU without that Dixie. Then it tries another one, and success. It was able to remove that one as well. The third one here, we'll see, failure. So that means when it booted, it didn't make it to Linux. So it crashed somewhere in between, which means that Dixie was a load-bearing Dixie, and it couldn't be removed. But we might try again in a future round. So we'll keep going, iterating through these Dixies and trying to move each one by one. So obviously, just booting the image isn't a strong enough test. Your test script should verify the network still works, all the memory is up, all the bases are there. So yeah, Dixie Cleaner is an automated system to remove redundant Dixies and free up space. It's all automated, but takes about a weekend to run on real hardware. We've seen it strip out over 200 Dixies from some images, and it significantly improves the boot time because there's simply less code to run. Now I'll go over what we call the anatomy of a UEFI firmware image. So a firmware image contains a number of firmware volumes. Usually a firmware image at least contains 2 firmware volumes, one for the Dixies for the drivers, another one for the PEI modules. Each firmware volume contains multiple files, and each file contains multiple sections. For example, a section might be the name of the file, it might be the version string, and almost always you also have the contents of the file itself. So this is a bit different from the Unix model, where a file is basically an inode, basically metadata plus the contents. In UEFI you have the metadata like the GUID, but then you also have multiple sections, and you can have an arbitrary number of sections in your file. So to make things a bit complicated, UEFI has an interesting way of compressing the entire file system. So with LZMA compression, what is most commonly used, because it's a fairly good compression algorithm, you can't compress a firmware volume itself. You can only compress a special type of section. And the way they get around this, and the way they're able to compress the entire firmware volume, is to nest it inside of that special type of section, as you can see here. This drastically complicates a parser, because you now have to recursively descend through these sections, looking for more firmware volumes. So it took a bit of work to get this to work properly in UTK. However, we were quite proud in the way we organized our code to make it parse this kind of structure cleanly, and it's fairly easy to extend. So what can UTK do? So for one, it provides all the file operations you'd expect, like listing files, reading, writing, removing files. On top of these primitive operations, you can build more sophisticated tools, such as the Dixie Cleaner we saw previously, also tools for validating firmware images. So I'll go over a few of these use cases. So first here you can see the UTK Table command. So you pass in a firmware image, and it will print all basically the tree that you saw earlier, of all the files and their GUIDs, their file names, the type of file, and the size. This is fairly useful information. And you can see here, this is just a screenshot. It's cut off. Usually this information is a few pages long, because there's oftentimes hundreds of GUIDs and files inside of the firmware image. And you can see on the left, you can see the hierarchy of the tree based on the indentation level, which it's a very convenient command to get a good grasp of the layout of whatever file system you're looking at. And there's more commands for poking around. We have the find command. You could pass in a file name or a GUID. You can even use regular expressions. So oftentimes shell is capitalized, or sometimes it's not capitalized. So using regex is a pretty useful tool. And when it finds the GUID or the file name, it will dump a JSON output with a bunch of useful metadata. There's also a dump function, which, like find, it will find based on the regex or the GUID, but it will rate the output to the given file name. So you could dump the contents of a file. Furthermore, we have the count command. This is what we use to count how many Dixies or how many PEI modules are inside of the firmware image. So it gives a summary of some useful information about the count of various items. So those commands you just saw are for reading from a firmware image. We also have commands to write back to a firmware image. We have remove, which removes a file from the firmware image based off of its name or GUID. Once you run one of these commands, use the save command to write it out to another file. So usually you read from one file, perform some operations, and then save it to another file. So as you can see here, we have remove, there's replace. So replace is useful for Linux boot, because we can replace an application like the shell with a Linux boot binary, Linux binary, and then we can save it as a new image, and oftentimes that just works. There's no other work we have to do to support Linux boot besides that. We have replace FFS, which is the same, but it's a bit more generic for other file types. Another useful operation is repack. Oftentimes, firmware images are per file compressed, rather than the per volume compression I mentioned earlier with the nested firmware volumes. The per file compression is a lot worse than the per volume compression because it doesn't make as good use. You can't share the LZMA dictionary between different file entries. So the repack command converts a firmware volume which is using per file compression to one which is using per volume compression, and this usually saves a megabyte or two of space inside of the image. And this is the chain of commands. It's very useful to chain multiple commands together. This will make sense of the syntax I mentioned earlier. Each command, such as remove, replace, save, they'll take a fixed number of arguments. You can write one command after another in one invocation of UTK. The output of one command is fed into the input of the next command. So in this example, the first line UTK ROM image, that will load. It will load and parse your UEFI image. Then the next line, it will take that image and remove the IP dixies. Then the next line will take the image from the previous line with the IP dixies removed and further remove the DHCP dixies. So it's kind of a pipeline of commands. And then finally at the end, you save the image. So this is often this pipeline you see here, this example is often what you need for Linux boot. You often need to remove a couple of dixies that Linux makes redundant in order to make enough room to insert the Linux kernel. And then you replace the shell of the Linux kernel, and it's a Linux boot compatible system. Oh, and there's one more thing, the IUTK GUI. So this stands for the Interactive UTK Graphical User Interface. So if this interface, it runs in your web browser, we're able to compile the Go code which UTK uses into WASM, WebAssembly, which runs with JavaScript and can be used from your web browser. We have a nice GUI front end. We're still working on it to make it more polished, but so far it looks pretty nice and it's sort of easy to use, but still needs a bit more polish. So in the future, look forward to our GUI environment. And we also have a new command, GUID to English. So this is convenient if you work a lot with log files, which contain GUIDs. What it does is it will parse your log file, find all the GUIDs, and add the English representation. So for example, Fiano contains a map. So for example, in this in.txt, you see there's a number of GUIDs. Most people won't recognize those GUIDs, but when you pass that file through the GUID to English, it will augment these GUIDs with their file names. So Fiano contains a mapping of over 1,000 file GUID names, and that mapping is derived from the UDK2 source code. So in summary, UTK makes it easy to script UEFI image editing tools. It's all written in Go, it's unit tested, it's type safe. It allows you to avoid rebuilding entire UEFI images, also other applications such as security, enabling Linux boot, and performing a general Dixie removal process. So how can you get involved? All the source code is openly available online on GitHub. It's fairly easy to download and try. First you have to install Go, you go get it, and you can run it as a binary on your development machine. If you want to get involved and contribute, we have many help wanted tags inside of GitHub, inside of the issue tracker, which are good getting started tasks. I recommend you join Slack. That's where a lot of the discussion surrounding UTK happens. We also have a chapter in the Linux boot book, which is a great documentation on how the UTK internals work, and some other things you can try. And if you want to try out UTK on your own firmware, please let us know how well it goes. If you run into any issues, please file bugs on a GitHub tracker, and we could try and fix those and improve the UTK command in Fiano for everyone. And finally, I'm not able to hand out stickers today, but you could download them on your own and print them off at github.com/linuxboot/stickers. Alright, thank you for listening, and I hope you all have a great and enjoyable rest of the day.